Okay, let's dive in. Today we're unpacking quaternions, often written as math BBH. Now, this is a four-dimensional number system. Sounds maybe a bit strange, right?
Yeah, a bit strange, but um, totally essential if you really want to get your head around 3D space and movement.
And the story behind them is fascinating, too. It involves this mathematician, Sir William Rowan Hamilton.
Right. He had this decade-long quest. He was trying desperately to create what he called an algebra of space.
An algebra just for 3D space. Makes
Yeah.
sense.
Yeah, using just three numbers, triplets, he called them. But every single time he tried,
It just didn't work.
exactly, failed every time. The issue was something mathematicians call zero divisors.
Zero divisors.
Yeah.
Okay, what does that mean in simple terms?
Basically, you'd have two non-zero numbers, multiply them together, and poof, you get zero.
Ah, okay. And if you have that, you can't reliably divide things.
Precisely. And if you can't divide, your algebra isn't much use for, describing how things move or relate in space.
So this is where it gets good. Hamilton's walking along the Royal Canal in Dublin, October 16th, 1843.
And suddenly the epiphany hits him. Just like that.
He realized he needed four dimensions, not three. A number like Q equals a plus pi plus CJ plus DK doll.
Yes. But to make it work, he had to do something pretty radical for the time.
He had to ditch commutativity. The idea that 6 times dollars is always the same as all the times 6.
Cornerstone of algebra for centuries.
Yeah.
And the legend says he was so struck by it, he actually carved the core rule into the stone of Brougham Bridge.
The famous Thai dollar is just J2 equals I2 equals IK equals I dollars 1 on. Wow.
And that one rule defines everything. It lets the quaternions split neatly into a scalar part, I also sort of the magnitude, and a vector part, pi dollars plus CJ plus DK day, which points in 3D space.
But that I dollars honor part, that forces the non-commutativity, right?
Yeah, so it leads directly to rules like IJ day, but if you flip the order, DK sign changes.
The order you multiply matters.
Critically. And this isn't just some abstract mathematical game. It turns out this non-commutativity is, well, it's the natural language of rotations in 3D.
You can actually see this yourself, can't you? Like with a book.
Yeah, perfect example. Take a book, rotate it 90 degrees forward around the x-axis, say. Then rotate it 90 degrees right around the y-axis. Note where it ends up.
Okay, got it.
Now reset it. This time, do the 90 degrees right rotation first, then the 90 degrees forward rotation.
Ah, it ends up in a completely different position.
Exactly. The order of rotations changes the outcome. Our physical world is non-commutative when it comes to rotations.
So the math has to be non-commutative too.
Which is precisely what quaternions give you. That's why they call it a non-commutative division ring. You can multiply, you can divide, but order is crucial.
And this is why they've made such a comeback in tech.
Oh, a massive comeback.
Yeah.
Especially unit quaternions, the ones with a magnitude of 1, they encode 3D rotations perfectly, multiplying them like 2Q with those models, doing one rotation, then another.
So why them over, say, the old Euler angles, roll, pitch, yaw? We use those in flight sims, robotics.
Well, the big killer for Euler angles is gimbal lock.
Right, I've heard of that. That's when things get stuck.
Kind of. It's a singularity. If two of your rotation axes happen to line up, you effectively lose a degree of freedom. Your system can get confused, unstable. Not good if you're controlling a drone or a spacecraft.
Okay. And quaternions.
Immune. Because they operate in 4 dimensions, they just sidestep that whole gimbal lock problem completely. It's much more robust.
Makes sense. Reliability is key. Is there anything else?
Speed. Computational efficiency. If you need to combine lots and lots of rotations, like complex simulations or graphics,
Yeah.
multiplying quaternions is just faster than multiplying the equivalent 3x3 rotation matrices. We're talking like 16 multiplies and 12 adds for quaternions versus 27 multiplies and 18 adds for matrices.
That adds up quickly in heavy computations.
Definitely saves processing power.
So stepping back a bit, this structure, math BBH double, it fits into a bigger mathematical picture, doesn't it?
It does. There's something called the Frobenius theorem. It basically says there are only a few fundamental types of number systems, norm division algebras, over the real numbers.
And quaternions are one of them.
Yep. You have the real numbers, math BBH. Then the complex numbers, math BBH. Then quaternions, math BBH. And finally, the octonions, math VB. That's it.
And there's a pattern there, isn't there? A trade-off.
A really neat one. To get the complex numbers from the reals, you gain a dimension but lose the property of order. Numbers aren't just bigger or smaller.
Okay.
To get quaternions from complex numbers, you gain 2 dimensions, but you lose commutativity, like we discussed.
And for octonions?
You gain 4 more dimensions, but you lose associativity. meaning A times B times CD isn't always the same as A times B times C. Things get really weird.
So each step up in dimension requires sacrificing a fundamental property we take for granted.
Exactly. It's like that user metaphor you mentioned. Reality is a simple line, our intuition, surrounded by this complex 3D world. To model that complexity, we need math that gives up simplicity.
Which brings us to a final thought, maybe something for you to chew on. If the math needed to describe 3D space requires us to sacrifice commutativity, does that hint that maybe the fundamental fabric of reality itself is inherently non-commutative? Think about quantum mechanics, quantum spin, stuff that behaves in really counterintuitive ways, like needing a 720-degree turn to get back to where it started.
Right. Is non-commutativity baked into the universe at its deepest levels? That's the question quaternions seem to pose.